Hi, and welcome to part 2 of exam 3 for Dr. Ko's class. Before I actually jump in and try to solve anything, I just want to review what we did back in part 1 of exam 3, which is where we developed the Lewis relationship. If you have not seen it, I would highly recommend going back and understanding how we got to this and developed it, as we are going to be using it here in part 2 to fully explain the issue at hand. And so what the Lewis relationship is telling us is pretty much that the heat transfer coefficient divided by the mass transfer coefficient is equal to the density multiplied by the heat capacity of the system. And so we will be using this in order to solve the second part of the equation, which is how we are going to explain how this Lewis relationship can be used in an energy balance to determine the relative humidity between the wet and dry bulb temperatures of the system. And so now that I've gone through and explained that, we can start going in and really dividing and understanding this second part of the exam. And so what we need to do is that we really need to firstly set up the energy balance of what we will be looking at from the inlet to the outlet. So starting on the inlet side here, where we have the air coming in, all that, we are going to have to start with the heat vaporization constant. I always fumble with that one. Heat of vaporization constant, and this will be for pretty much evaporating whatever that liquid is going into the system and at how fast of a rate it does evaporate. And so this will be multiplied by the mass transfer coefficient, how much of a mass is going in and out of that system, and this will also be multiplied by the total difference between the concentration at the surface minus the concentration at some point far away, denoted by the infinity sign. And so this will be the inlet of our energy balance for this equation. And so, before I'm actually moving further, this is the concentration of water at the surface and at some point far away from the surface, just for clarification purposes. And so now we need to set this equal to the outlet side of our energy balance. And so this will be equal to the heat transfer coefficient multiplied by the temperature. I'm trying to think of which way it is. Is it far away or is it? It's far away because it's inverse of this. So this will be multiplied by the temperature of water at some point far away minus the temperature of the water at the surface. So the way I always remember is that this side's always the inverse of what's on the left side. For the concentration of the surface minus the concentration far away, on this side it's the temperature far away while minus the temperature of the surface. And so now that we see this, what we want to do, and it might not be inherently obvious at first, but how this is going to help us significantly is that we're going to divide this over here. And so we will actually have that heat transfer coefficient divided by the mass transfer coefficient that we calculated from the Lewis relationship previously. And so this actually allows us to rewrite this equation as the heat of vaporization multiplied by the concentration at the surface minus the concentration somewhere far away is equal to the density times the heat capacity, because we can substitute this in for what would be this, multiplied by the temperature difference between some point far away and the surface. And so this is what we are actually given after we take that first step of condensing and really just involving this Lewis relationship that we will need to use for calculating the relative humidity. And so now we have this equation here where we have heat of vaporization multiplied by the difference between the concentration at the surface and some place far away is equal to the energy outlet, which is the density times the heat capacity multiplied by the temperature difference between some point far away and the surface. And so what we really need to do is that we can look at this and we can tell that because this is an ideal gas, we can change the concentration values, and we can also change this density value so that it's actually more representative of the pressures and the partial pressures that are in the system. And so this equation can be rewritten as lambda, the heat vaporization, multiplied by the saturation temperature of water, P sat of water, and this is right there, and this is also going to be the P of partial pressure of water some point far away. This is at the surface. I would denote that. Partial pressure of saturated water at the surface minus the partial pressure of the water at some point far away. And this is going to be all over the gas constant multiplied by the average temperature. And so this will also be showing a similar change on the right-hand side of the equation compared to the left-hand side as well, where we're going to be replacing this rho Cp, the density times the heat capacity, and instead of having that anymore, we're going to have the total pressure of the system. So we'll be looking at P total multiplied by still the temperature differences between some point far away and the surface. That's not going to change. Also divided by the gas constant multiplied by the temperature average. And so this is now a way that we can include and incorporate the wet bulb and the dry bulb temperatures in this equation. And so that's not inherently obvious either, but it's reflected by these partial pressures of the water, both at the surface and at far away from the surface. And so next thing we can really look at and see is that these two cancel out on both sides. And that'll also be very helpful because it really condenses it, makes it look a lot prettier. And then when we do that, when we cancel this out, we are going to have to multiply by the heat capacity on the right side yet again. So this will be condensed down until lambda heat of vaporization multiplied by the difference between the partial pressure of saturated temperature of water at the surface minus the partial pressure of water far away from the surface. And this is equal to the total pressure multiplied by the change in temperature between the surface and a point far away multiplied by the heat capacity. And so this is actually the equation that we're going to use to compare the wet bulb and the dry bulb here, is on this one. And so really the last thing we have to do for this part of the exam is we need to just develop our relative humidity equation. And so from this, we can actually look at some of these values that we would be getting, such as this difference here, and we would get what we can develop into a relative humidity equation. And so the relative humidity that we will be wanting to calculate is going to be this partial pressure of the saturated volume right here. This will be the bottom in the denominator, whereas the partial pressure of the water at the surface will be on the numerator. So easier to look at it like this probably. Partial pressure of water at the surface minus the divided by the saturated partial pressure of the water also at the surface. And so this is actually the equation that we wanted to look at, and this is also going to be reflecting on the temperature of the water that is there as well. And so actually no, sorry, one mistake I actually just caught myself doing is that this is actually not for the partial pressure of the surface, it's the total partial pressure at any point of the water. And so still the water at whatever that temperature of the water is. And so once we take this partial pressure at the surface divided by the saturated partial pressure of the water, we can then find the relative humidity that is in the system here. We found this once again by using the Lewis relationship that we found in part 1. The heat transfer coefficient over the mass transfer coefficient is equal to rho Cp. We incorporated that here and condensed it and changed around the equations a little more to find this, which relates the two wet bulb and dry bulb temperatures. And we took these values from what we find here and we can put that into our relative humidity equation, and gives us this, where we take that partial pressure of the water at the surface, divide that by the partial pressure of the saturated water at whatever temperature water is at that point, and that gives us a relative humidity. And so we will use this further in part 3, 4, and 5, and I will look to see you in the next part of the exam video. Thank you.